Hello everyone, this is Mike Dowding with the SD Mines Physics Department, and we're going to finish up Chapter 8 today with a few more example problems, specifically utilizing the idea of energy lost due to friction, which we have in a previous video, we defined that as thermal energy. And in the last video I promised that we would do our best to kind of put everything together into one problem. And when I say everything, I mean as much of the previous course materials as we can. And I think what we'll be able to do is probably include everything except for circular motion. So what we're going to do is we'll go back to the inclined plane of some angle theta. And we'll start with our mass at the top of the incline. There will be some friction in the system. And unlike other problems where we had to test to see if we had enough applied force to overcome static friction, what we will do is we'll just assume that we do have some initial velocity. We'll make this 2 meters per second downhill. And then as our mass displaces down the length of the incline, there will be work done. Energies will change. Velocity will change. So when we get to the bottom of the incline, there will be some final velocity that we would like to solve for, but at the same time we have to consider everything that's happening, including work done by forces, changes in energy, how much those energies are going to change based on the way that the system is behaving. And it may look like there's a lot of things here, and there are, and we may not be sure as to where to start. So we'll just start from the beginning. And since this is a chapter based on conservation of energy, we will look at the energy at the initial location, which I will call E naught. So everything here is going to be the combined kinetic and potential energies at the initial location. And then down at the bottom, once we've reached the bottom of the incline, we'll call that E final. And no matter what happens in our system, conservation of energy has to be maintained. So the energy in the system at the initial point has to equal the energy in the system at the final point. And there will be some combination of kinetic and potential energy down at the bottom point. But because we are considering friction, we're expecting there to be some roughness to the surface itself. There is also going to be some thermal energy that is generated. And so our final energy needs to be a combination of all three of those values. So let's see what it is that we want to solve for in this problem. We'll put a few more given pieces of information in here. We'll say our mass is 10 kilograms, and we'll use a coefficient of kinetic friction equal to 0.25. So I would like to know if the mass does make it all the way down to the bottom of the incline, how fast is it going? And if it doesn't make it to the bottom of the incline, where does it stop? Okay, so this is going to be a conditional problem here. We either want to know the final velocity, or if we end up stopping somewhere, what is the final displacement value? Right, and I'll call that little d, because if we don't make it the full way down the incline, then it can't be the full displacement. But we'll say that this incline is 5 meters long. Alright, I think we have enough information. Our next step is, since we're comparing the energies between the initial, oops, didn't want to do that. Since we're comparing the initial energy to the final energy, what I really need to do is figure out which location do I have more information about. And if we're not sure, then we'll just go ahead and start filling in what information we do know into the equation that we're going to be using. So this is the equation that we're going to be using right here, our conservation of energy equation. We'll clear all this other stuff out for now. So what do we know? Do we know anything about the initial kinetic energy? And kinetic energy is 1/2 mv squared. We do know the mass. We do know the initial velocity. So yes, we do know the initial kinetic energy. The initial potential energy will be based on the initial height of the block. And when we say height, we need a measuring point. We need a 0 point for the measurement of height. And in previous examples, we have allowed the lowest point in the problem to act as our 0 point. We can choose any location that we want to be the 0 point, but whatever we choose, we have to stick with that labeling. And the reason I want to let the lowest point be the 0 point is so that everything else in the system is positive. So that means our initial height is some height h above the 0 point, but I don't know what that height is. Well, just because we don't know something, don't let that stop you. We can still write it out as part of the equation. Later on, hopefully I'll be able to find what that value of h is. And then we can do some more work in this expression. Now for the right-hand side of the expression, if we get all the way down to the bottom of the incline, if we have any kinetic energy left over, that kinetic energy will be based on the final velocity of our mass. But if we get all the way down to the bottom of the incline, our final potential energy at that location will equal 0, because that is where we labeled the potential energy to be 0 in the system. And lastly, we have any thermal energy that is generated by friction as our block slides down the incline. So we'll go ahead and put in what we know. And we're going to take a moment to figure out just what that thermal energy should equal. In our previous video, we said that the amount of thermal energy that is generated by a friction force will equal the absolute value of the work done by that friction force. And this has to be a kinetic friction force. Static friction will not do work. Okay? Static friction always does work of zero. The reason for this is that you don't have any displacement when you're dealing with static friction. The whole point of static friction is that you don't move. So we should never have to ask ourselves the question how much work static friction does, because that answer should be zero. But our kinetic friction, well, our kinetic friction will do work in the amount of Fk dot d. So big D was the displacement that we would have down the incline. And I'm going to draw our mass at some arbitrary point as it's sliding down this incline, because as we slide downhill, our friction force needs to oppose the direction of motion. So our friction force is uphill, and while we're at it, we may as well put in all the other forces that are acting on our mass. And we need those other forces because our definition of friction force is coefficient times normal. And so now we need to know what the normal force is. And if you go back in your notes to some of the previous problems that we've had with inclined planes, you'll remember that the weight has to be broken up into components, and it is the component of the weight that is pointing perpendicular to the incline that equals the normal force. And looking back in your notes, you'll see that that normal force is equal to mg cosine theta. So there's our friction force. It's mu k mg cosine theta. We need to plug all of that in right here. And we have to dot that with the displacement vector. Now that dot product is going to be hiding an angle relationship, which I am going to call angle phi. Phi and theta are not the same angles. Theta is the angle of the incline. Phi is the angle that exists between the two vectors in our dot product. And if we look back at our diagram, our friction force is pointing uphill, our displacement vector is pointing downhill, so phi has to be 180 degrees. Cosine of 180 is going to produce a -1. And so we have work done in the amount of negative mu k mg cosine theta. And, whoops, I forgot, we also have the displacement value, d. So all of that is the work done by friction. To get the thermal energy created by friction, all we need is to take this energy, which friction has stolen from our system, and we put it back in as thermal energy. So our friction takes the energy away. That's the minus sign. Thermal energy, we're going to put that back in. So puts back energy, puts back in. mg cosine theta d. All right, there is the thermal energy that has been generated for this system. So our thermal energy is mu k mg big D cosine theta, and then we have all the other values, some of which we have numbers for, some of which we don't. Okay, well, first of all, what we should see here is that the mass is common to every term in the system, and so the mass of the block doesn't matter. It's going to factor out. But the other stuff, let's see what else we need. We should probably have a theta value. So I'll say 60 degrees. So we can plug that in. Out of all the things that we have in our equation, we know what theta is. We know big D. We know V initial. We know the M, but that's going to cancel out. And what we were looking for was the value for V final. We also have our coefficient of friction. We know what gravity is. But we're still missing one important term. We don't know what the starting height of our mass was. But if we look at this triangle long enough, it kind of does a trick. The height is one leg of a right triangle, and it just happens to be the leg that is opposite of our theta value, and big D is the hypotenuse of that triangle. So H can be described as big D sine theta, and we can sneak that in to our expression. Trying to use my eraser here. Well, kind of working. I'll just rewrite things over here. So we have 1/2 mv naught squared plus mg h is d sine theta equals 1/2 mv final squared plus mu k mgd cosine theta. Okay, so that looks like a lot of stuff, but as we said, the mass is going to cancel out from all of our terms. Don't want my G to cancel out. We're solving for V final. So let's see, we want to get everything else over to the other side. So I will subtract mu k g d cosine theta. We need to multiply both sides by 2. So when we do that, we get V naught squared plus 2, and I'm going to factor the GD's out of those two terms. And what we're left with is sine theta minus mu k cosine theta equals V final squared. And then our final step is to take the square root of both sides so that we can get V. Now, we're taking a little bit of a risk here in assuming that our block is actually going to make it the full distance D. the way we've set up our equation is we're assuming that we're going to make it the full 5 meters before we run out of kinetic energy. So what happens if we go through all of this and we end up with a negative sign underneath our root? Well, that means we did our work wrong by making that assumption. But who knows, we might get lucky with this, and we may actually have the mass make it all the way down to the bottom. But if it turns out we go through all of this hassle and we do solve for an imaginary answer, that's not the end of the world, because we said that if that's the case, then the alternative question that we need to ask is, where does the velocity equal 0? And we can actually update this equation pretty easily to answer that question. Remember, this whole thing was set up to solve for v final, so if I forced that to equal 0, all I would have to do is update the equation for the displacement that would cause this to happen. And then I would just rearrange the whole expression to solve for big D, whatever that is. But we'll see what happens. This is the risk that I take in making up numbers for some of these example problems, but we'll just see what happens. So, initial velocity. Go back so we can see things here. Initial velocity was 2 meters per second. So we have 2 squared plus 2, 9.8. Big D was 5. We have sine 60 minus 0.25 cosine 60. And all of that should equal the final velocity when we get to the bottom of the incline. Get my calculator app open. Okay, so I have just calculated this portion, which came out to equal a positive 0.741, and everything else in the expression is going to result in a positive outcome. So I now know that I'm going to get a real answer. It's not going to be imaginary, and so I can keep going. If I had gotten a negative out of this quantity here, then I would stop and go back and consider the alternate answer that we were considering. But since we know we're going to get a real answer, we'll keep going with our calculations. And I am getting an answer equal to 8.76 meters per second. Okay. Oh, so we have our velocity at the bottom of that incline. What else could we do? Since we know what our final velocity is, let's ask what's the final kinetic energy of the system. And we can do that by plugging in the mass that we never bothered to use because we didn't need it. 8.76 squared times 10 divided by 2. That gives us about 383 joules worth of energy. Let's compare that to the kinetic energy that we started with. We started with 1/2 mv0 squared, and the initial velocity was 2. So let's see here, we're getting, what is that, 20? So the change in kinetic energy, final minus initial, is 363 joules. So what does that mean? Well, we know that the change in energy has to equal the net work that was done in the system. And since we know that the change in kinetic energy was 363 joules, that tells us what the net work done in the system is. Now, if we compare that to the work that was done by friction, friction does negative work. Friction always does negative work. And if we put numbers into that, we had, let's see, negative 0.25, 10, 9.8, cosine of 60, and the displacement was 5. So we can actually tell numerically how much work or how much heat energy was being produced by our friction force. And this actually isn't that much. We have negative 36.78 joules. And you compare those two, and obviously they're not the same thing. So how can we have so much more energy being put into the kinetic case when we only took this much energy away for friction? And the thing to remember is that net work has to be the net combination of all work done in the system. Friction is just one force in the system that is doing work. The fact that these two numbers are so vastly different implies that there is at least one other force in the system that is doing work. And if you look back at the diagram, one of those forces got erased there, and that was the important one. If we look at the normal force is perpendicular to the displacement, and so it's not going to do any work. But gravity does have a downhill component that is pointing in the same direction as the displacement, and so gravity will do work. And because our gravity component is pointing downhill, gravity will have to do positive work. So, if our net work was 363 joules, and we had negative 36.78 joules of work done by the friction force, what must be the amount of work done by gravity? And to answer that question, we just need to take the difference in the values. So we will add the 36.78 to the other side, which is going to give us 399.78. So I'll round that up to 400 joules. 400 joules worth of work is what gravity has done. Now, maybe you want to do a quick little self-check to see if gravity has in fact done that amount of work. There are two ways that you can confirm that answer. I'll draw the system here again. Now, our displacement is downhill. Our gravity force is straight down, but it has a component that is pointing in the direction of the displacement, and that's the component that we want. But that downhill component, that is mg sine theta, and that downhill component is pointing in the same direction as the displacement vector. So our dot product just produces mg sine theta d. And you might be asking, well, where's the cosine? Well, this is the downhill component of the gravity force. And if I take the dot product of two vectors that are pointing in the same direction, the angle between those two is 0. So I would get cosine of 0, and all that results is mg sine theta d. Okay, let's see what we get. We get 10, 9.8, sine of 60 times 5, and it looks like I've got a little bit of a rounding error here, but I'm getting pretty close to 400. But I did promise that there was another way of getting the same answer. The other way that we can try this is keep in mind back in chapter 7, when we talk about work, we said that only force in the direction of displacement will do work. Well, we could kind of flip that around, and we could say that only force in the direction of the component of displacement will do work. Our displacement vector has x and y values, and our gravity force is pointing along the vertical direction, which, well, we called that h. So what would happen if we took mg and dotted it with h? In that case, both mg and h are pointing in the same direction, so we get mgh, but mgh, h was equal to d sine theta. So we're getting the exact same thing as what we got up here. And like I said, my answer is off a little bit because of some rounding that I've been doing along the way. That's my fault, but this will work. I'm getting something closer to like 420 joules, but I don't want to waste too much time trying to backtrack, figuring out where the error is, because I do want to get to another example, if you don't mind. So there's quite a bit that could be done here. I know this is probably overwhelming looking at everything at once, but one step at a time. with the conservation of energy. Start here, start putting things together. So the other problem that I wanted to consider, let's take another inclined plane. We will start our mass at the top from rest. We will assume that it overcomes the maximum static friction. And then at the bottom of the incline, there is a spring, which is currently at rest. So the spring is at its equilibrium position. This block is going to slide down the incline. It's going to collide with the spring, and it will compress the spring some distance, little d, past the equilibrium position before momentarily coming to a stop. Okay, let's put some numbers into our system here. We'll go back to another 10 kilograms. We will have the angle be 45 degrees. Typically I don't like using 45s, but we'll use it for this one. And yep, so we've got an initial velocity of 0. And we'll say that the maximum compression of the spring is 5 centimeters. And the spring constant will be 2,000 newtons per meter. Now again, if you remember from a previous discussion, spring constants are usually given in terms of newtons per centimeter, just because it's a more realistic measure. But we can't use that unit in our math. We need to have newtons per meter. But just in case we're curious, what would this look like as newtons per centimeter? That would be 20. So 20 newtons per centimeter. Okay. Well, that's quite a bit of information for a problem like this. And so now comes the part where I start asking questions, or at least I start asking you for the different things that I want you to solve for. Given the given information over here, I would like to know what is the total distance that the block slides down the incline, and we need a coefficient of friction in here as well. We'll do 0.1. So what's the total displacement down the incline? What is the height of the incline? Actually, no, we won't ask that. We'll just ask the total displacement down the incline. And then when the block actually impacts the spring, I want to know the velocity of the block at impact. So how fast is the block going at impact, and what will be the potential energy stored in the spring during that final compression moment. Okay. Of all the questions that we have posed to us, what we need to do in terms of conservation of energy, we can compare the energy at the initial location to the energy at any other location in the problem. And as it turns out, there are actually two different locations that have kind of grabbed my interest. We have the impact site and we have the final compression site. So three different locations: initial, impact, and final. And we have questions posed to us that relate to all three of those locations, but we can only compare the energies of two of those locations at once. We can compare E naught to E impact. We can compare E impact to E final. We could compare E naught to E final. So we just have to kind of make up our minds what we want to do, where we want to start. And typically that means seeing which of these locations you have the most information available. And so E naught, the initial site, would have energies based on the initial potential energy and the initial height. Now we know what the initial kinetic energy is. It should be 0. But what was the initial starting height? Now looking at this problem and comparing it to the previous problem, we could say, oh, well, H would just be d sine theta again. And that is correct, except your H value is going to change based on the compression of the spring. So are we going to be measuring H from the rest position of the spring or the lowest point that the spring achieves during compression? And either one of them is perfectly fine. My preference, again, is to go with the lowest point in the system. So I'm going to let the absolute lowest point in the system be the 0 point for gravity. And then I'll measure H from there. But this means that little d is a part of big D. If I define things using the lowest point for H, then the total displacement that the block slides has to include the compression distance of the block. Now that's okay. We can always incorporate that value of little d into the total displacement. But now this is valid as well. So we have an initial energy in our system that is equal to mgh, which is equal to d sine theta. So that's the initial energy. I know the mass, I know g, I don't know big D, I know theta. So, well, that's why we were asked to solve for big D. Let's try the energy at the impact site. before we do that, let me come back up here. And if you notice, all of the energies that I considered were only the energies associated with the block being at this location. While the block is at this location, what is the spring doing? Well, the spring is just hanging out at its equilibrium position. And how much potential energy is a spring going to have sitting at its equilibrium position, where x is essentially 0? Well, in that case, the spring potential would be 0, and that doesn't change anything for the energy at E0. But at the impact site, when the block gets down to the impact site, what's the spring doing? Well, it's still at its equilibrium position. And so we can still say that the energy in the spring is equal to 0, because the spring has not displaced yet. We will have some non-zero velocity associated with the impact. And our potential energy at the impact site is going to depend on how high above the 0 point we are. So keep in mind, when we impact the spring, that was when the spring was up here at the equilibrium position. So we're still some tiny little amount h above the 0 point. But hey, h and little d make a smaller right triangle, which just happens to be a similar triangle to the larger one that we've been using. And so the height at the impact site, h, just ends up being the compression distance, little d, times our angle, sine theta. So there's the energy at the impact site. Now, I know what theta is, I know what little d is, I know m, I know g, but I don't know the impact velocity. And that's one of the things that we were asked to solve for. So let's move on to the final location. What happens when we reach that maximum compression point? When we get to the maximum compression point, that should be K final. When we get to the final compression point, we stop compressing because we stop moving. So our final kinetic energy is 0. Our final potential energy due to gravity, now that we're down to the lowest point, that's where we've defined our gravity potential to be 0, so that's 0. But now is where we actually get to include a value for the energy stored in the spring. The spring has finally displaced from its equilibrium position by a distance of d. And that means that the energy stored in our spring is 1/2 the spring constant, little k, times the compression distance squared. And this was one of the questions that we were asked, or at least I asked, be solved for. And as it turns out, that's the only energy that we have at the final location. So let's plug in numbers. We have 1/2 of K, which was 2,000 newtons per meter, times our displacement, 5 centimeters, is 0.05 squared. Calculator time. And I am getting 0.25 joules. Is that right? Seemed kind of low, but well, that might just mean that we have a very, very small incline. All right, well, that's the total energy in the system. Not very much. But that means that we now have to have 0.25 joules for the energy at the other two locations that we've considered. So now we can say that the total displacement is 0.25 over mg sine theta, and our mass was 10, 9.8 for g, sine of 45. Oops. Trying to write off the side of the screen here. Sine of 45. All right, well, this isn't going to be very large. Maybe I should have picked bigger numbers, but too late now. 0.25 divided by 10 divided by 9.8 divided by sine of 45. Yeah, if I'm doing this right, I'm getting a total displacement value of 0.003 meters, which would be like 3 millimeters. So yeah, looks like I dropped the ball on choosing values for this problem, but let's see. Yeah, that's not going to work out very well for us because the total compression distance of the spring was 5 centimeters, and this is telling us we can only go 3 millimeters. So what I'm going to do is, let's see here, perhaps if we reduced the mass of our object, we'll do 0.1 kilograms instead of 10 kilograms. Right. I don't like having to doctor my numbers here, but we want something that's going to be realistic. Okay, we'll try this again. 0.1 kilograms. Okay, this gives us something that we can actually work with. So I'm getting 0.36 meters, or 36 centimeters, or we can say that the block was released 31 centimeters above the equilibrium position of the spring. Okay. And let's see here. In my haste to put all of this together, I completely forgot to incorporate the friction into this problem. So I have already screwed up the numbers. I don't want to tempt fate and screw up more stuff here, so we'll just keep going with what we have. We'll solve this for a non-friction case, and then at this point I think we've seen enough examples that if you need to, you can incorporate friction into these equations. You're just going to have a little bit more to include into these two statements because you'll have work done by friction as part of the final energy values. But that leaves us with one more value to solve for, which is the velocity at impact. And solving for the impact velocity, we have 0.25 minus mgd sine theta. Then we have to multiply by 2 and divide by the mass, followed by a square root. So hopefully this doesn't get messed up either, but now that we have a total displacement that actually works, hopefully we don't get an imaginary expression here. So we have 2.25. This needs to be divided by the mass, but then we can actually cancel out the mass on the next set. -45°. All right, so we have 0.25 divided by 0.1, and that 2 acts on everything. So we have 2.5 minus good, 0.34. So we're going to get something real. I am getting a final velocity of 2.07 meters per second. Okay. So, considering the example problem that we had on the incline with friction and no spring, and then considering the problem that involved no friction and a spring, can you now incorporate the two systems so that you have a spring and some friction? And basically the setup for the two systems as far as conservation of energy is concerned is pretty straightforward. The one thing that we have to keep in mind now is that there are two different kinds of potential energy that we have to consider in our problems. We have potential energy due to gravity, we have potential energy due to springs. And each of them require knowledge of where the 0 point is. And for gravity, we can sort of choose where we want our gravity potential to be measured from. But for springs, we don't have that luxury. We have to use the equilibrium position as the 0 point for our springs. If you want to use the same location for both, you can do that, but it has to be the 0 point for the spring. So we would actually have to move this 0 point up that value of little h. But when we do that, when our block drops below the 0 point, then it will have negative potential energy when it drops below the new 0 point. But that's okay. We can deal with negative signs. Alright, that is the final video for Chapter 8. Get started on the homework if you haven't already. If you have, get the homework finished. See you at the Chapter 9 video.